Hello, everyone. Thanks for joining us today. My name is Morrison. I'm the Managing Director of Research here at IBHS. And today I'm joined with my colleague, Dr. Faraz Hedayati, our lead wildfire scientist here at IBHS.
Good to be with you.
Yeah. So today, really what we're going to focus on is the building blocks leading us forward in the wildfire space. So we're going to go and take a little bit of a step back and look at how wildfire science has evolved over the last 25 years, maybe even beyond that, and where our current understanding of wildfires and how we can mitigate the damage is at and how we're moving forward. So I'll just start off with really IBHS itself. And so we built the research center in 2010, but even before that, we had conducted some wildfire research really with the Witch Creek Fire post-event investigation in 2007. And really, for the last, when we opened the research center, we did a lot of research looking at embers, how they attack building components, and what have you. We've partnered with the Forest Service to look at how fires spread through fuel beds, how trees ignite and the embers that are produced by that, and what are their physical quantities. And more recently, we've really looked at the problem of suburban conflagration in a lot more detail and looking at structure-to-structure fire spread and what are the dynamics that occur in those types of situations. So I think where I'd like to start off is really looking at what was the state of wildfire science back in 2010 when we opened the research center? So what do we know about wildfires and what was kind of the state of the art back then?
Yeah, our understanding of fire back in 2010 was mostly influenced by the internal compartment fire dynamics. And that is basically the amount of oxygen is limited or the amount of fuel is limited in a compartment fire. And when we go to the field or like to a wildfire kind of situation, none of those are limited. So we have infinite access to both of those. So the laws don't really transform from that understanding into this. And that was a big gap back then that IBHS started to bridge in addition to our Ember research.
Yeah, and talk to us a little bit about embers. It was, as I mentioned earlier, a real focus for us really from the start of when we started doing our research here at IBHS. But really, what did we know about embers and why were embers so important to us back then?
Yeah, there were a few European colleagues back in the 60s, late 60s, who were focused on the ember problem in Southern Europe, Portugal, and Spain. They started a collaboration with US Forest Service during that time. And the product of that collaboration was a few models that our member companies use right now that looks at ember transport, and based on that, what is the threat of embers. So basically, they look at their mass, their size, their temperature to model the risk or the hazard side of it when embers fly and create a threat into the built environment.
So let's talk a little bit about that threat to the built environment. How have we seen that in the field? How does that manifest itself in terms of the hazard?
Yeah, so embers can accumulate in different parts of the parts around the home and ignite that, and then that could be vegetation or any amount of flammable material around the home or the building itself, right? So when we include this indirect and direct ignition by embers, it becomes the leading cause of damage in the community is because of embers.
Yeah, absolutely. So IBHS built the research center, and really one of the focus was wildfire in terms of what the perils we're looking at, right? Wind, wildfire, wind-driven rain, and hail. And so really starting in 2011, we really started building our capabilities to produce embers. So, and the original concept was based on some of the work that NIST had done. Talk to us a little bit about the state-of-the-art research when we started making our ember generators at IBHS.
Yeah, prior to this collaboration with NIST, there were ember generators used by colleagues in the fire science community, but none of them were sophisticated enough to produce a range or like we can control the flow of those. So during that time, around 2010, Dr. Steve Coles worked with NIST, and the first generation of ember generators were developed back then. But there was no wind-driven environment that those could be tested. So the ember generators were shipped to Japan, and then they had a full-scale facility in Japan back then that was like a several feet wide, several feet tall. They put a sample in it, and then one ember generator could fit in that, and the experiments start looking at that. Yeah. And there is obviously a gap between that scale and what we see in the field.
Yeah, absolutely. So this is a picture here of the first generation Ember generators at IBHS. You can see a much younger Dr. Ian Giamanco, our lead meteorologist here, and they're really looking at this generator. And so this is really what we saw with the Ember generators. And I remember we had people from the fire service from California here, and I remember they were jumping up and down because they're like, that's exactly what it looks like in a real type of environment. But really the purpose of this research was really doing and showcasing what you were saying, is how do embers attack the building? How do they ignite the different combustible materials around the building? So you can see here we have, debris in the gutters which has been ignited by embers. We had the mulch ignited by embers, and ultimately that really ignited the structure as well. And so I think we got a better understanding, but I think to something you said earlier about understanding how embers interact with a building when there is wind, even for that facility in Japan, it can't capture the full dynamics in a structure. So why don't you talk about kind of where one of those unique abilities at IBHS is to better understand the embers and how they interact with the built environment?
Yeah, the diversity of knowledge that we have here at IBHS between wind engineers and fire engineers and civil engineers gives us a good platform to study this kind of behavior, right? So we see here that where do embers accumulate? There is a glowing line at the base of that wall. We ignited the structures unwantedly a few times, and then we realized, oh, the interaction between these buildings or these components are very important. Something that cannot be captured in a reduced scale experiment.
Yeah, absolutely. And so at this point in our research, we really did, and this is actually a picture of that, is we were really focused at vents. And we were looking at how does embers attack vents? How can embers get inside the building? And once they're inside, what are the risks that they can pose? And so that was one of the real key aspects that is really where I started doing some work in the fire space. My background is in wind engineering, as you know. But I remember long days inside that building with Dr. Steve Quarles, where we were collecting embers, counting embers, looking at the size of the embers that were able to enter through these different vents and characterize the risk potential. Because you can get a lot of embers in through a gable end vent that like here, and when they get into an attic, especially if you don't have a basement, what do you put in your attic? All your extra stuff. And what do you put that in? Cardboard boxes, right? So we were really trying to quantify that risk of ignition. The other aspect is where embers get caught on these vents, on these complicated structural details, embers get stuck, and they can start actually directly igniting the structure.
Yeah. So, and that's a very important element that, like the roof system, if it's not Class A, embers can land on it and ignite it. The base of the wall, again, it's a system. It's just not the base of the wall. It's what is around it, what is the wall material. And when we put all of those together, we start seeing a pattern that we see in the field.
Yeah, absolutely. And it's a really great point. We actually had to put non-combustible board there at the bottom because we kept igniting this building right at that interface of the floor where the embers collected. So that ember research really took us through 2017 here, and that's about the time that I think you joined IBHS. So and we started focusing less on embers attacking the vents and started looking at the embers attacking all the other stuff around the building. So why don't you take us through kind of the next 2 or 3 years of research looking at those elements?
Yeah, in 2017 or around that time when Dr. Steve Quarles retired, it took 2 people to fill his shoes. I took the lead on the research on decks when what he started in 2015. And then here is like, he's recording like this dynamic here. We see where embers accumulate on the surface of the deck and actually where do ignitions start. And he realized that the gap between the deck boards above the joist is the weakest spot on the deck that ignition happens. And this is something that cannot be captured in a small scale. And later on, I looked at how embers fall between the gaps and ignite materials underneath. So we have both above deck and under deck thermal exposure. And we see that the building codes that were designed for deck safety, for lack of a better term, they don't work because that only looks at the walking surface of the deck, not the entire deck assembly.
Yeah.
And this research showed us that how important are those, and we proposed a new way of evaluating decks based on this research.
Yeah, and I think you really found the importance of the joists actually in this. So talk to me a little bit about that.
Yeah, well, when joist ignites, it can carry the fire in both ways, like in lateral or towards the building. And then by that definition, the fire is built on several components, not necessarily one component. Something that we saw repeatedly in our research later on, but it all rooted into these kind of dynamics of how things come together to create a next level threat.
Yeah, I think that's really important. And one of the real reasons IBHS built this research center is to really fill gaps, right? We didn't design this research center to be a standard testing lab, but we also built it to make sure that how we evaluate our materials, our building products, is actually mimicking what's happening in the real world, but also the dynamics of the realistic failures, right, or how ignitions ignites. And I think the point of this system level approach is something we'll be talking a fair bit later on. But again, making sure that we're making sure those test standards are mimicking reality. There's always going to be assumptions.
Yeah, on this specific topic, the decks were 2 feet by 2 feet and only the walking surface and at the no wind condition. If you change any element of those, that we did in this test campaign, we see that the standards do not address the vulnerability.
Yeah, that's a good point. If you make the deck bigger, it actually ignites and actually poses a very severe hazard to the house igniting.
Absolutely.
And ultimately it can be destroyed because of that. Around this time too, we kind of increased the amount of partnerships that we did have, and we had our first partnership with the U.S. Forest Service here, where we were looking at fire spread through fuel beds and looking at ember sizes from vegetative fuels. So walk us through kind of the goals of that research and really what we found.
Yeah, the U.S. Forest Service Fire Lab in Missoula, they have a wind tunnel that is like much smaller than what we have, and they tested what is the width of the gap that is needed for the fire not to jump from the burning side to the other side. And fire doesn't scale well. Right, so they had to generate the same dynamic in a larger scale. So at IBHS back then, we started looking at fire spread between a burning fuel bed with a gap to the next one. So basically look at what is the necessary width of that gap. And we saw that the gap between the extreme of their capability and the lowest end of ours is something that was not studied, and actually that's very important.
Yeah, I remember that. I remember talking about trying to match the data sets and getting consistency, and they couldn't go fast enough and we couldn't go slow enough.
Yeah.
So we had that gap in the middle. At the same time, in terms of our built environment work, we started focusing a lot more on building components and actual man-made features like fences. So talk to us a little bit about the kind of the research that we were doing on these different building components at that time.
Yeah, building on specific building materials, like the walking surface of the deck, we got into building assemblies, and that was, as you mentioned, the vent screens, fences, or like decks, a little bit on windows back then, as Steve Coles led the research on that. And then that was on the material side. We also looked at some of the active mitigations, like the importance of gels. Right, those were also, or like intumescent paints. Those were also some questions that were addressed back then, looking at the performance of different building materials. And then we realized when we go in the field that performance depends on what is happening around the building as well, rather than the building itself.
Yeah. So by this point, I mean, we'd been doing active research for eight or 9 years, and our colleagues had done a lot of work outside of IBHS too,
Absolutely.
and we had gained, the scientific community had gained a lot of understanding, but at that point there was still a gap between the great research and science that we knew, and really the built environment and where kind of the rubber meets the road a little bit of what is the relative performance of these different building materials? What are the mitigations that happen? So that really led us to build the Suburban Adaptation roadmaps, trying to take this science and actually put it into a digestible form that actually could be used by people in a practical way to enhance mitigation. So Talk to us a little bit about that process. It was a very long and arduous process. I remember being in way too many meetings with you for way too long on that process. But talk to us a little bit about what we were trying to accomplish and where we ultimately ended up.
There was a gap between where the science stopped and what was the need of the insurance industry. There were clouds of information on the performance of different building components, and that was it. So through this framework, we built a flow chart or several flow charts for different building components, and then ranked what is the best one, what is the worst one, and what is in between. And through this dynamic, we could incorporate the importance of different building elements. And that was the first time that a framework was created to address, again, the specific need of our members.
Yeah, absolutely. And I think this was really almost somewhat of a rank ordering kind of process in terms of deciding what were the most important components and were they poor, marginal, good or best, right? In terms of that. And it was a challenging process, right? I remember a couple times for me, ultimately I said, this one or this one, which would you rather, to really cut the spread, right? In terms of which one was more important. So we rolled this out in 2020. We published this in 2020, of course, in the middle of COVID. I remember having a celebratory beer over Zoom with you as we launched it, because this was really almost a year of pretty intense work for us overall. So why don't you provide me kind of what was the reaction of the insurance industry, homeowners, and the scientific community once we published this?
Yeah, when we were developing this, we wanted to make sure that the framework that we are working on is not biased, right? So we invited external collaborators, Jack Cohen from US Forest Service and Alex Marangidis from NIST. Both are well-known figures in wildfire science, that we double-checked the way that we were looking at this. And then when we pushed this out to the public and colleagues on the technical side, the feedback that we got was so into the details that was confirming to me that the framework is actually can work to discriminate the performance of different building materials. There were questions like about why do you draw the line between a 4-foot tall deck versus 5, right? So those were kind of the detailed question that they were not a big deal, basically.
Yeah, it's an important point, and one of the challenges of really in any field is translating the cold, hard scientific facts into a usable framework, right? You're always going to have to make more practical choices, right? Was it 4 feet or 5 feet, right? And really, I think the point was really getting where does it really matter? Where are the largest areas of separation between performance of different building materials, right?
Yeah.
And you have to sometimes just draw a line somewhere.
Yeah.
So while we had these great frameworks and we could make some different decisions in terms of what building component or what roof cover might be better than another roof cover in terms of a relative form, really talk to us about kind of the gap that still existed from the perspective of how do we mitigate these wildfires? Yeah,
so basically the flow that you see here, if I have 4 or 5 red elements on the building, what is the first one that I need to retrofit, right? So those were the questions that the Suburban Adaptation Roadmap could not address. So the next logical step was to look at this from a holistic perspective. And the decade of research that we had at IBHS in post-event investigations and basically what we had what we saw in the chamber tells us that some of these elements, some of these components need to be put together in order to provide a holistic reduction into the risk of the structure.
Yeah, absolutely. And that really was the next step, is where we worked on what ultimately became Wildfire Prepared Home. And so this time we sat in a conference room in Asheville and we really talked about these different flowcharts in the Suburban Adaptation roadmaps and talked about how do we package them together? What are the most important aspects to have holistic or system-wide mitigation of the wildfire to really meaningfully pull down the wildfire risk to an individual structure?
Yeah, so when we were testing different building components against embers, we realized that it's such a chaotic environment. Even at the controlled condition that we have in the test chamber here, we can control the ember generator intensity, the wind flow, all of those is like under our control. Still, it's such a chaotic environment that embers can go into the attic, at the same time land on the roof, and at the same time ignite the base of the wall, right? So when we see a risk like that, then we realized there are components that should put together that are vulnerable to embers, and there are components that needs to be put together for flames.
Yeah, absolutely. And so from the scientific perspective, we really did put together all the components for ember mitigation into kind of the Wildfire Prepared Home base. And then Wildfire Prepared Home Plus is really protecting the structure against, the flames and the ember attack. I think the other important point as well, from more of a kind of a implementation or almost business aspect, is the relative cost between the two mitigations, right? I mean, Wildfire Prepared Home Plus requires dual pane tempered glass windows and siding. If you don't have those elements already, that's a fairly expensive retrofit for your home. Whereas the ember protection really, I think, is much more of a lower cost and maybe more accessible to existing structures.
Yeah, a lot of it. Most buildings already have Class A roof. That's an expensive piece, but it's already installed, so there is no extra investment on those. Protecting openings, mesh screens for the whole structure can be below $100 to $200. So it's fairly affordable. And the next big piece is Zone 0, which is more on the maintenance side than like investment. So there is like continuous keep up on the property to make sure that those elements are there. Yeah. And by doing those, we can reduce the vulnerability of our homes against embers, something that we know that will happen during an event.
Yeah, and those elements in Zone 0, there may need to be changes in their landscaping, which may be a cost, but relative to trying to reside, it's a much lower cost and a lower barrier to entry. So once we did this, we turned our focus really back to the research, and we did a little bit of a pivot in the research, or in our direction of research. We focused a little bit away from the ember, not because we solved everything we ever did with the ember, but really at that time, starting in 2000, the suburban conflagration, particularly in Paradise, really put a much clearer focus on structure-to-structure fire spread. So talk a little bit about that pivot of our research at that point.
Yeah. So when embers ignite a few structures in the community, and then when flames get vertical, and when we add wind, then the fire spread becomes flame-driven, not necessarily ember-driven. And within like about 10 minutes or 15 minutes, when the homes are close together, it can consume the whole and move forward. That was something that we saw in the field during the glass fire, during the campfire. We repeatedly saw that kind of pattern. And because of the capabilities that we have here, IBHS is the only organization that can study this kind of wind-driven fire. And then we started that research working with different organizations.
Yeah, so I think we partnered with the Forest Service, with CAL FIRE, with NIST, and really started to look at sheds and really starting to look at what you would almost call outbuildings. And if they ignite, what hazard do they pose to your house or really potentially your neighbor's house?
Yeah. So we took a divide and conquer approach for this project. We tested garage-size sheds. The photo that you see here, our colleagues at NIST tested like a smaller closet size or very small sheds under no wind condition. So what we saw here was that the interaction between the structure or the components and flames is very important, and it's chaotic. It doesn't follow the typical understanding that we have from fire, that fire always goes up, stays, and dies out. That was not what we saw. And based on separation distance and the collapse of the shed, this dynamic changed a lot.
Yeah, absolutely. And as we were really conducting this research, the tragedy in Lahaina occurred with that devastating fire. And we conducted a post-event investigation a couple of months after the fire. And talk to us a little bit about some of the data we collected, how some of the research that we had done at the lab focused the variables we were looking at, and ultimately, what did we learn from that tragedy?
Yeah, when we were in the field, we realized that regardless of the resilience of different building materials that were in the field, all of them were destroyed, basically the photo that you see here. That told us that the exposure from the fire, the thermal exposure, is so high or was so high that building materials did not have a fighting chance. Regardless of what they could offer, they were overwhelmed. And that structure or that observation formed a framework in our minds that we need to look at it in a way that how can we give building materials a fighting chance? And by looking at the elements or analyzing the data that we collected in the field, we realized the exposure can be collapsed into structure density and connective fuels, and the resilience is basically on building materials.
Yeah, absolutely. It was really. I was with you in the post-event investigation in Lahaina, and it was really striking on the effect of connective fuels that they had and what could be a connective fuel. Right. I think before that, if you asked us now, we would kind of say, of course, cars can be a connective fuel, but it was really what we saw in Lahaina that kind of hammered that home a little bit to us as well.
Yeah, and maybe we had seen it before in the campfire or other fires. In Lahaina, it was so evident that as people were evacuating, they jumped onto one car, so there were a lot of vehicles left behind. And to your point, we saw that and was like, this is different. This is playing a role into the exposure to intensify fire, and then we quantified it later.
Yeah, absolutely. And so at the same time, we really started our second collaboration with CAL FIRE, and we brought in different partners: University of Maryland, University of Berkeley, or UC Berkeley, sorry, FSRI, and NIST, and we kind of upgraded the shed experiments a little bit. Yeah. So talk to us a little bit about what that next step was.
At the time that we finished the shed experiments, those were the largest experiments ever done in WUI fire research on a wind or even structure-to-structure fire context. And while that was the largest one, it was a narrow kind of heating towards a specific point on the target building. It taught us a lot of information that we didn't have before, but that simple fuel load that we used, those wood creeps, didn't allow us to stretch the findings into basically what you see here in the background. So the next logical step for us was to increase the fire size, build residential auxiliary dwelling units filled with realistic furniture, and then look at the threat of that burning structure onto the target building.
Yeah, and I think one of the really interesting things that you were able to find after doing several of these experiments was how the choice of building materials can play a dramatic role in the exposure that building has to the downstream neighbor. I think all of the ADUs that you see burning here were Chapter 7A compliant, but how you achieve that compliance can be different a little bit. And so we had buildings that had combustible siding, and we had buildings that had stucco siding or non-combustible siding. And so talk to us a little bit about how those different material choices can change the exposure for downstream buildings.
Yeah, the sequence of experiment or ignition that we had here, we ignited those wood creeps, and then that overwhelmed the windows and doors on the windward side of the ADU, regardless of the siding material. So the moment that this building becomes an active fuel load depends on the weakest component. But it doesn't stop there. Based on the other partial materials or partial resilience that this building has, the exposure that this one creates on the next building down with is a function of, to your point, the cladding material. Yeah. We saw that when we use Chapter 7A compliant, but stucco versus wood, the flame surface area or the extension of the flame is very different in these two cases, which impacts the heating pattern on the downwind structure.
Yeah, absolutely. And through all these experiments, really one of the things that, as being a wind engineer by training, we always talk about return periods of the hazard, right? Or what's the probability of this failure? And I don't think that it was surprising to me at the time in talking to you is that sort of framework didn't exist in the wildfire space in terms of abilities. So talk to us a little bit about how the experiments that we were done helped us really try and start kind of looking at this wildfire mitigation and in terms of a more probabilistic way.
Yeah, this takes us back all the way to the beginning of the discussion, Maury, that a lot of our understanding on fire science comes from compartment fires. When the fire goes the standard curve. When we ran these experiments, we realized as the fire intensifies in the shed or in the ADU, the roof collapses or the side door collapses. So the heat, instead of going towards the target building, goes sideways, or it limits the oxygen access. So at the peak of the fire intensity drops. So we have a very dynamic curve. That deviation from the standard fire curves and this makes the traditional metrics that we have to give us the probability of failure. Right? So within this framework, we looked at an intermediate time scale rather than this instantaneous or several minutes, and that could tell us what is happening beyond total loss or no damage, and allowed us to create a framework that tells us what is actually in between.
Yeah, I think this is an important point is when we often characterize damage in after post-event investigations, it's major destroyed, major damage, minor damage, unaffected, kind of these bulk categories.
Yeah.
But we're not able to actually use that in engineering terms to actually know how much we buy down that risk. I think a little bit of what we talked about earlier in wildfire, the Suburban Adaptation roadmaps. This is really what you would have loved to do from a scientific perspective, right? It would kind of solve that problem 4 feet or 5 feet. Well, the 4 feet is 20% and 5 feet is 21%,
yeah.
Right? That's the actual kind of that. So, through these experiments, I think we in this probabilistic framework, we developed Wildfire Prepared Neighborhood, and this is something that the feedback we heard from members when we developed Wildfire Prepared Home is, well, what about the community, right? What about the community? And wildfire, unlike other natural perils like hurricanes, your neighbor matters a whole lot more to the survivability of your home, not just the actions you take in mitigation, but what the community does as a whole for mitigation. So talk to us a little bit about the framework and approach we took at generating Wildfire Prepared Neighborhood that really wasn't possible back in 2021 when we developed Wildfire Prepared Home.
Yeah, all these sequential development in our vision of how to get there were necessary to basically to get where we are right now, that we can develop something like Wildfire Prepared Neighborhood. What we saw in the field, the exposure matters a lot, and that is dominated by structure separation, distance, and connective fuel. Environmental aspects are also important, but we cannot control those, right? So based on what we can control, what is achievable, we develop Wildfire Prepared Neighborhood, and we put requirements for separation distance, for connective fuel, that if X percentage of homes do not have these requirements, then that neighborhood or that cluster of home is not qualified for this. And based on those dynamics, we also looked at on the resistance side, what is the building materials that is used on the community, and we developed the framework.
Yeah. Yeah, and I think it's an important point for everybody to understand is Wildfire Prepared Neighborhood isn't designed to prevent all ignitions. It's really to try and prevent conflagrations, these devastating fires that take out entire communities. That our goal is to prevent those, and rather than have really the disasters we saw in Lahaina, in the Eaton fire, and the Palisades fire, is to really limit the amount of damage and prevent uncontrolled fire spread between different homes in a neighborhood.
That's a great point, yeah.
Yeah. Okay, we've covered a fairly long road and ground, and really going back the last 25 years of wildfire science and really mitigation. I think really thanks to a lot of the research of a lot of people and collaborators within the wildfire community and IBHS, we've come a long way at really creating the framework and creating kind of how we can actually mitigate against these wildfires and really start minimizing their impact on our built environment. So as we move forward, what do you see as the next hill to climb, if you will? What is next for the research, both at IBHS, but also in a much more broad sense in terms of wildfire research that is needed to help move us forward?
Yeah, the ADU experiments that you saw a video, we repeated those experiments 11 times. we have a good understanding of the fire dynamic for Chapter 7A compliant structures. The next phase of this experiment is to look at non-code compliant buildings to see what is the difference, and that addresses the vast majority of the housing stock in the US. And through this, we are looking at risk in a different way now. To your point, wildfire is not a hurricane-driven phenomenon. It's not an external factor that dominates the whole exposure. It happens at the local level. It happens at the balance between resilience and exposure from the surrounding structures, something that we can alter. And through this research, the framework that we developed and the next stages of this, we are actually trying to look at the risk at that local level. That provides a lot of hope for homeowners in California and other wildfire-prone areas that we are not powerless. By changing those, even in existing communities when structure separation cannot change, by removing connective fuels and by strategically retrofitting specific building components, we can at least stall, if not stop, the chain of conflagration.
Yeah, absolutely. And I think one of the other next kind of things that we saw, and it goes back almost to the DEC standard there, where through these experiments, we saw the role of convective heat transfer in terms of as the hazard or how fires can actually spread from one building to the other. Talk a little bit about some of the research where we have to look at down that vector.
Yeah, when we were running these experiments, we used two different instrumentations on the target building, one that measures the total heat flux and one that measures only radiation. And we realized that actually between 50 to 90% of the total contribution to heating is by convection, not radiation. Something that no fire spread model actually captures right now. And that's on the hazard side. On the building material side or the resilience side, if we give the same amount of heat to potatoes, one of them boiling, the other one roasting, we get two different products, right? This is something that is completely brand new. There is no setup in fire science community that can replicate convective heating. And IBHS, after this observation, is investing some of the resources on that to develop a machine or a setup that can study convective heating.
Okay. Well, Faraz, I really appreciate the time here today, have this conversation, really taking us all the way through from really the start of us understanding wildfires prior to IBHS doing research, all the way through a lot of the work we've done here, but also a lot of the work done by other collaborators, ultimately with the goal of really making us have stronger communities and mitigate the threat of these wildfires. So,
yeah.
So thank you very much for joining me today.
Good to be with you. Yeah.
Thank you.